Okay, so this is something kind of familiar but kind of new. So a Cartesian product is a way of combining two sets to generate another set. Okay, so it's kind of like well, it's nothing like, but I mean, we've seen this kind of idea before. You can take two sets and form their union, that's a new set. You can take two sets, form their intersection, that's a new set. To take two sets and do a relative complement, that's a new set. So a Cartesian product in that sense is you're combining two sets to create a new set. So how does this work? So the elements of A, now I might say Cartesian product, I might say times, but this symbol means Cartesian product, are what are called ordered pairs. Now it's a very important ordered, because unlike sets, where order is not important, in this there is an order. A is first and B is second. So the first part from A and the second from B. So you're going to have, okay, so a pair, it's two things, and the first part of it is going to be from A and the second part is from B. So for example, if C is the set of counties that begin with C, and W is a set of counties that contain W, then Cork Down is an element of this. So it's a pair, two elements, the first thing in the first set and the second thing in the second set, and the Cartesian product is all of the possible pairs you can make. Now, one thing that's very important is we use round brackets to signify that the order is important, because the set containing Cork and Down is not the same as the ordered pair Cork Down, where order is important. So more precisely, the Cartesian product of A and B, you can write something down, but really it's going to be in examples that you understand it. It is a set, because as we said, we're going to combine two sets to form a new set. So it is a set containing ordered pairs. So we write it like this. So it's a set of ordered pairs such that the first thing is in the first set and the second thing is in the second set. And you form all possible ordered pairs is the Cartesian product. Okay. So spoken A times B, or the Cartesian product of A and B, is the set of all ordered pairs A, B, such that A is an element of A and B is an element of B. In other words, all possible pairs of B. Okay. So the word order is important. Cartesian product of A and B is not the same as the Cartesian product of B and A. If A and B are different. If A and B are the same, yeah, then obviously they're the same. A set, we've said a few times, you can do everything in terms of sets. So if you want to do an ordered pair in terms of sets, you can do it like this. So it's kind of the thing the first thing is on its own, and then the second thing is in there. So you can kind of get an order like that, but we're not going to do that. Okay, let's see some examples of Cartesian products. So a deck of cards is like a Cartesian product. So that V be the set Ace, 2, 3, 4, 5, 6 up to 10, Jack, Queen, King, and S be the set of suits, hearts, spades, diamond, clubs. An element of this set, V, Cartesian product S, so the Cartesian product of the values and the suits can be chosen by first picking a value and then a suit to give a value suit, okay? And then this is the set of cards in the deck. So for example, the Ace of Hearts is take the value ace and the suit heart. And if you wanted to, for example, include jokers, and usually you have two jokers who are different, you would take the Cartesian product, so that's all your 52 cards, and then the jokers aren't in there. So if you form so all the elements that are either normal cards or jokers. So note that certainly when A and B are finite, the cardinality of A Cartesian product B is equal to the cardinality of A times the cardinality of B. This is something that we've probably seen before, certainly with decks of cards. So think about V times S. How many cards do you have in a deck of cards? You have 52. And this is the same as the number of values times the number of suits, which is 13 times 4 suits, which gives you the 52. So this is going to be something that you'll use. The number of elements in the Cartesian product of A and B is the number of elements in A times the number of elements in B. So a deck of cards is an example. Another example is a chessboard, which is another example that I'm missing here, which is a spreadsheet. It would be a Cartesian product. All the cells, like say if you talk about, we'll do a little one here. So you got columns, and say if we just take 3 columns, 1, 2, 3, 4 rows. So the set of cells could be, let's say, now we usually do horizontal, vertical, and indeed that's what they do. So they call this, for example, B2 in a spreadsheet. So the set of cells is equal to the Cartesian product of the set ABC with the set 1. I'll just write 1 dot dot 4 because I'm in trouble with space. So the number of cells here is the number of things here by the number of things here. Number of elements here, 1, 2, 3. Number of elements here, 1, 2, 3, 4. 3 by 4, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So a chessboard is also a Cartesian product. So that L in a similar way to this. So L is the letters A, B, C, D up to H, and N is numbers 1 to 8. In this sense, set L, Cartesian product N consists of pairs letter, number. Using coordinate system, you can see this is the set of chess squares. And this indeed is where you have a coordinate system, is where you would have seen this notation before. These are also coordinates, and in coordinates the order matters as well. So we can talk about a chess square, say this one. We can write it as, it might be written in chess notation as C5, but for us we would write it as C, comma 5, ordered pairs with round brackets. Okay, so we'll do a little example here. Question. So let A be the set containing 1, 2, 3, 4. B be the set 3, 4, 5, 6. It would be nice to see a universal set here, but we mustn't need it. And X the set containing A and B. List the elements of A intersection B Cartesian product X and the elements of A Cartesian product X intersection B Cartesian product X. What can you conclude? Okay. So again, if you're finding something that's complicated, maybe build it up slowly, work within the brackets, for example. So first we're going to find, if we're finding this, A intersection B. So these are all the things that are in A and in B, and my recommendation is go through everything that's in A and see is it in B. Is 1 there? No. 2 there? No. 3? Yes. 4? Yes. So that will be the intersection. Only 3 and 4 are in A and in B. Now we need to do a Cartesian product of 3, 4, Cartesian product X, which is AB. So it actually probably makes sense to write these out again up here. So the intersection is 3, 4, Cartesian product X, which is the set containing A and B. Now what we have to do is make all possible pairs, the first thing in here and the second thing in here. This is what we have to do. And it is a set as well. So we'll put it in set notation. Now probably the easiest thing to do is do 3A, 3B, 4A, 4B, and maybe we check the number of elements. We should have, when we're finished, number of elements in here times number of elements in here, 2 by 2, we should have 4 ordered pairs. So we'll make sure we check we've got 4 ordered pairs. So so let's do this. So 3A, we use roundy brackets, 3A. Sorry, that should be a small a. And then 3B, roundy brackets, indicating order is important. And then do 4A and 4B. You have to have the roundy brackets, otherwise you haven't included order. It's not an ordered pair. It's not in the Cartesian product. So this, as we said, should be a little a. Okay, that's fine. And there's 4 elements as we expected. Now let's do the Cartesian product of A and X intersection the Cartesian product of B and X. So this will probably be a little bit messy, but let's go. So Cartesian product of A and X, we must form ordered pairs. The first thing is in A and the second thing is in this. So we'll do 1 with A, 1 with B, 2 with A, 2 with B, 3 with A, 3 with B, 4 with A, 4 with B. So let's go. We get 1 and A, 1 and B, 2 and A, 2 and B, 3 and A, 3 and B, and finally 4 and A. Well, I'm saying A, it's the ordered pair 4A, and then 4B. Okay, so what I'm doing here is I'm building this up, but I'm going to work with the things in brackets first. So that's the Cartesian product of A and X. Now do the Cartesian product of B and X. It's going to be kind of similar. Again, roundy brackets. So 3 and A, 3 and B, 4 and A, 4 and B, etc. So 3 and A, 3 and B, 4 and A, 4 and B. 5 and A, 5 and B, 6 and A, 6 and B. Okay, so that's the first bit there. And now what we need to do is we need to do their intersection. So the intersection of these two is the things that are in this set and in this set. So my recommendation, let's just write that down, is to go through the first set and check off the things that are also in the second set. That's probably the easiest way to do that. And it's a set, so use the set notation. So what is 1A in there? No. 1B in there? No. 2A? No. 2B? No. 3A? Yes. 3B? Yes. 4A? Yes. 4B? Yes. So it's just these elements. Now there's no more because it has to be in both of them. So you don't have to consider any of these because they're not in there. So we get 3A, 3B, 4A, and 4B. Okay, very good. And then the question is, what can you conclude? Well, if you're paying attention, you'll see that this set and this set are actually the same. Now this is an illustration, but not a proof of the fact that these two things are equal. It's probably a little bit difficult to prove that they are, but they are. So you get this kind of A times X as such, intersection B times X, almost like multiplying out. Now it's kind of a law, but we won't pursue it any further. Okay, another example. A very basic protocol, so something maybe that a website is doing, asks for a letter from ABC and a digit from 0, 1 for a password. List the elements of L1 Cartesian product D1, the set of possible passwords. So let's form all the ordered pairs. The first thing a letter, the second a digit. Hence or otherwise write down this. And then a more advanced protocol asks for a letter from A to Z and a digit from 0 to 9. Set of possible passwords for the advanced protocol is the Cartesian product of these two. Write down the number of possible passwords for this advanced protocol. Okay, so first of all, let's list this and we'll put it in a set. So as before, if you're doing a Cartesian product, do the first thing with everything in here, second thing with everything in here, and keep on going. Ordered pairs, roundy brackets. So the ordered pair containing A0, so like the password then would be A0. A1, B, on to the next one, B0, B1, C0, C1. Okay, so that's the done. They're all the possible passwords. Now, you say, well, oh, the roundy brackets aren't part of the password, and I appreciate that, but you're kind of thinking about this representing B0. And of course, in the password, order is important. So you do need these ordered pairs with roundy brackets. Hence or otherwise write down this. So hence means just using this. This is the number of elements in this set. And there's 1, 2, 3, 4, 5, 6. So you have either 6 by counting, or use the fact that the number of elements in a Cartesian product is the product of the number of elements in the first set and the number of elements in the second set. And here we have 3 letters, 2 digits, 3 by 2 equal to 6, same answer. But you could just count. But for the other one, you couldn't really count because like for each letter, you got A0, A1, 8 to 9. So you got 10. There's 260. Well, that's giving the answer away, but there's 260 possible passwords. You're not going to write them all out. So you need to know this kind of theory here. So the number of elements in the set L2 Cartesian product D2 is equal to the number of elements in L2 times the number of elements in D2. A number of elements in L2, you got 26 letters here, times number of digits 0 to 9, 10, 260 passwords. Okay. Right, a little bit more down here. So the plane. So R, remember, is all the possible real numbers. So basically you're thinking kind of a number line actually. From plus infinity to minus infinity. The set R, Cartesian product R, which is also written as R squared, consists of all pairs x, y, such that the first element is a real number and the second is a real number. As I said, R can be visualized as a number line. So what we're going to do here is we're going to make a connection with the coordinates that you know about. So this would be plus and this would be minus. Okay, the plane is nothing but two number lines kind of put together and a coordinate system. So given a scale, each element of the Cartesian product, the plane, can be associated to a point in the plane, and we said at each point in the plane can be associated to an ordered pair. So R cross R, for example, say, so this is a pair of real numbers, say for example minus 1, minus 1.5. If you've got a scale, you'll be able to go to minus 1, minus 1.5. So along the x and along the y, and it's a Cartesian coordinate system, which means it is rectangular coordinates is the word, and then that point there represents that point there. So that's something you have actually seen before. And similarly, if you take a point on the plane, measure how far along it is the x, measure how far along it is in the y, they're both real numbers, and so the point on the plane gives you an ordered pair, first thing a real number, second thing a real number. That's an ordered pair, that's an element of R, Cartesian product R, which we also write as R squared. So this R squared is a notation for the plane. Plane meaning infinite flat space. It's also possible to take the Cartesian product of two sets, A times A Cartesian product B, and take the Cartesian product of this with another set C. So for example, you could talk about A times B, Cartesian product with C. Now what would this be? This would be the set of ordered pairs, the first thing in AB, A Cartesian product B, but that itself would be an ordered pair. So the first thing coming from here, well, these are ordered pairs. That's the first thing in your big ordered pair here, and the second thing would be something in C. Now it would have to be the case that for AB to be in A Cartesian product B, that A would be in A and B would be in B, A in A, B in B, and finally this would have to be in C. Now if you identify this thing with the ordered triple, you could just kind of drop the brackets here, and you could talk about A times B times C as the set of triples A, B, C, such that A is in A, B is in B, C is in C. So for example, R times R times R is the set of points in space, three-dimensional space. You need three numbers to specify a point. The order matters: distance along the x, distance along the y, distance along the z. So for example, if you go, say, distance A along the x, distance B along the y, and then go up a distance C, you've got a point in space, A, B, C. Okay, So this kind of stuff is going to be important for us for bit strings, passwords. We'll see a little bit of that in the next lecture.